Hello, Code Monkeys. If you were here about, 10 minutes ago, you saw me ramble my way through about the first half of a HeapSort program. So what we're doing now is we're trying to break that down into a more digestible chunk. So a lot of this is going to be review if you were here for that, but I did not want to upload that hour 40-minute monstrosity onto YouTube. So we are going to start with, very simply, what is a heap, and we're going to shoot for somewhere around the 10 to 20 minute mark. I think would be much more appropriate than what we ended up with. What is a heap? A heap is a binary tree where, every element bears the same relationship to its children as every other element. For the purposes of heap sort, that means that every element will be larger than both of its children. Numbers will tend to become bigger as you go up the tree, and they will get smaller as you go down the tree. So, really simply, 1, 2, 3, 4, 5, 6, 7 would be a valid heap if you wanted the roots to be smaller, but we actually don't, and I didn't think about that when I started making numbers, so let's just run that right on back. And we'll start with 7. Need white to draw. 7, 6, 5, 4, 3, 2, 1. Valid heap. And let's pick one number and change it. 0. Whoa, what am I writing? 0, 6, 5, 4, 3, 2, 1. Not valid. How are we doing on time? 2 minutes. Plenty of time. Okay, let's talk about traversing a heap. That could be interesting. Interesting or not, it's important. I think it's interesting. That's why I'm making these videos. So, if we... How do we want to start this? For reasons that will become apparent later, we are not going to be building our tree out of linked nodes. We're going to be using an array. And we'll keep those same 7 boxes we've always been using. 2, 3, oh, that one's really small. 4, 5, 6, 7. That's slot 0, that's slot 1, that's slot 2, 3, 4, 5, and 6. And these we will sort of conceptually represent a tree. This tree, 0, 1, 2, 3, 4, 5. Well, I guess 6 is still going to be there. 6. Okay, so the question is, if we don't actually have structures and pointers to other structures, how do we move around this beastie? Well, we can actually just move linearly, so we can move from 0 to 1 to 2. That's terrible, too. So we go there, there, there. Oh, excuse me. Sorry. It's there. Just kind of work that into our arrowhead. There, there, and there. And that's kind of the same thing as going like that. Kind of the same thing? It is the same thing. Speak with confidence, kids. It's important. Speak with confidence when you're confident. When you're not confident, don't speak with confidence. It's like lying. Okay, so you can actually just linearly move through the tree in either direction. You have some index number. For some reason, they usually call it I. And you can increment I, you can decrement I. And that'll move you around the tree either in the direction of the arrows or in the opposite direction of the arrows. And that's pretty cool and useful, but we also want to be able to follow these lines. How do we do that if we're not storing pointers to the next node? Well, got a handy dandy algorithm. So we're going to have a left child of each node and a right child of each node. I used to use n, but I think n's a little confusing. I think I'm going to use I for index, because then you don't get the index number confused with the actual contents of the node. I hope. So the left child of a node is going to be, if you look over here, you can see that it is twice the index number plus 1 will always give you the index number of the left child of the node. I guess you don't technically need parentheses there. And to get the right child of the node by its index number, I suppose is the correct way to say it, you're going to go ahead and multiply that index number by 2, and you're going to add 2. You will notice that all of the right children are just one more than the left children. How do you go backwards? The parent of any node by index number. Ooh, that's a little funky looking. That's okay. We're not going for artistic beauty here. That's a different channel. You're going to go ahead and take that index number, and you're going to subtract 1. And you're going to use the power of integer division. And the secret about integer division is that if you're taking two integers, a and b, and you got your little happy-dappy division there, c is going to be the largest number such that b times c is less than or equal to a. This is going to matter a lot in discrete math if you ever get there, but for programming purposes, just remember that it rounds down. Gets a little weird with negative numbers. Don't worry about that for now. We're working with unsigned integers. Now, we've got about 2 minutes left. What can we do with 2 minutes? We've covered traversal. We can talk about asserting a node if we're really quick. We don't need to land exactly on 10 minutes. Okay. So, in order to assert a single node, which is going to be the building blocks we're going to make asserting the entire heap out of, here is what we are going to do. We're going to use some fancy algorithms to decide what's smaller and what's larger than what. Single node, it's got 2 children. For heaps, our binary trees. Alright, so what we want to do is we want to examine the values of all 3 of these nodes, and we want to make sure that the largest one ends up at the root. We do not care about the order of the 2 children. As long as they are both smaller than the root, our goal is satisfied. So, we're going to need some tests. We want to make sure that, let me rephrase that. We're going to want to check the left child. And what we're going to check the left child for is, first off, is the left child... Let's not make the same mistake we made last time. That got a little confusing at points. We're just going to call the heap we're working with H, and we're going to denote the value of a node in H as H, I for index, All right, cool. So we want to check and see if h sub L of I is greater than h sub I. And if it is, we're going to want to swap the values of h sub Li, L of I, and need a closing brace too. Okay. Now, that is sort of the level 1 solution. The other thing we need to check is we need to make sure that h sub Li is greater than h sub R of I, because we only want to promote the largest number. And then the other thing we have to check is we have to make sure that these children actually exist. Now, because we are building this off of an array, there's a really easy way to check if children exist. What should we call the existence function? We're not actually going to write this when we write code, but we'll say if some node index I exists, then it is going to have to be, the index number is going to have to be less than the size. And you know what? I think we're going to go ahead and call the size the end number. How are we doing on time here? All right, 12 minutes. We got to wrap this up. See? End number. Now, in order to take a shortcut, we can rig our functions up so that we only check nodes that have children. And that means we will never have to worry if the left child exists. We can assume that. What we can't assume is that the right child exists. So, we are going to swap the left child up in the following condition. H of L of I, get our correct braces in here. H of L of I is going to be greater than H sub I. Give these eyes tittles, makes them look more like eyes. And, is it an and? It is an and. And the right child either does not exist, and because we are guaranteed to only be checking nodes that have left children, the only time the right child will not exist is when it's actually equal to the end number. Just to reiterate, our end number is, back when we built our array, add 4, 5, 6, 7. We have 7 happy boxes, numbered 0, 1, 2, 3, 4, 5, 6. We have 7 boxes, but we number them starting at 0. I didn't make that video on arrays that I had sort of half intended to. So, the number of boxes is 7, but there is no actual value at index 7. Really quickly, other languages will prevent you from checking index 7. C will not. You have to check for that yourself. Because we will have our array bounds set correctly, the only time the right child won't exist is when, for this particular heap, when the index of the right child is 7 is the only time the right child won't exist. I.e., it's equal to the end number. Okay, so if the right child doesn't exist, or the left child is larger... Oh, I'm sorry, that's not how you check that value. It's going to be... What are we doing in time? Oh, we really got to wrap this up. Okay, start moving towards an ending point here. Oh, come on. Get rid of that. There we go, perfect. Back to brushes. H sub L of I is greater than H sub R of I. Oh, that's getting hard to read in there, isn't it? I have one last thing there. Okay, then we're going to swap. H of L of I keep saying of when I shouldn't. I hope you're all tracking. And H sub I. Swap those. Okay. And then because we're going to have an if situation going on, we don't have to check as much for the right child. For the right child, we just need to make sure that it exists, and we will know it exists if R of I is less than end, and H sub R of I is greater than H sub I. And in that case, we will swap H sub R of I and H sub I. Okay, this gets confusing